Okay, so yeah, today we're going to definitely finish on lists because we started talking about stacks last time, and now we just have to talk about queues and then variations on those. And then we'll start on the next module, which is algorithms and algorithm analysis, which we've kind of been hinting out through all of these demonstrations. I've been showing you, well, if you do it this way, it's going to take hours to do or minutes to do, versus if you did it this way, you know, then it's going to only take seconds, right? We've seen that in practice, and now we're going to actually, you know, come up with a framework by which we can actually analyze that kind of stuff in a more formal way. Remember that we are online, so if you have any questions, you can go ahead and post to Piazza or to YouTube. If you have been watching online, you might want to, or actually, no, it's not during this time, but just a reminder that on Thursday, there is a student advisory panel from 11 a.m. to 1 p.m., and they've got pizza and stuff like that. I'll be there later, like at 12:15 or something, for the last half, but it's up here in Avery on the 3rd floor, and you can stop by and have pizza and share your opinions on the department, learn something about the department, whatever. All right. So just a reminder that that's on Thursday. So back to queues. Queues are a cousin to stacks in that they are a first in, first out. Typically, the way that you view a queue is, well, as the name suggests, it's a line, right? Things come in one end and then they go out the other end. We generally call this NQ, right? And DQ, right? QUE. There we go. Right? Sometimes sometimes the same names, push and pop, are used. I don't like to do that because it confuses it with a different data structure. Other times, something like, say, offer is used. You offer it up to the queue, and then pull. You're pulling the queue, POLL, for an element, right? The idea here again is if things go in like 10, 42, 20, and I don't know, 5, right? Then the order that they go in is the order that they come out, because it's just like a line. You get in the line, you don't have any line jumpers, you don't have any cutters or anything like that. If you get in the line first, then you're going to be served first, okay? And that is a queue. So here's our stack implementation from last time, where we use this underlying list here. And our idea was to use a linked list, and we'll stick with that idea here, and a whole bunch of other functionality that we implemented. I want to reuse that functionality, right? So one option would be to subclass this, but is a stack a queue, and is a queue a stack? No, that doesn't seem right. We definitely want to reuse this underlying list here. I don't want to wrap it up like an onion either, because if I just wrap this up using composition, just in terms of a stack, a queue is going to be completely different, because with a stack, you are working from the same end, pushing and popping at the same end. With a queue, you are doing it at different ends. So this is one case in which I will make a wholesale copy of this class and call it queue instead. UEUE. There we go. And let's open it up, and we're still going to have the same underlying list here. We'll also still support the a bounded queue versus an unbounded queue, but instead of push, we're going to have to rename these things. So I'm going to go ahead and name, if I put something into the queue, I NQ it, right? And it looks like we're going to be operating on the front of the line, right? If we're going to add it at the beginning. Right? If we add it at this end, that means that we're going to have to dequeue it from the other end, right? It doesn't matter if we switch these around as long as we are consistent about it. So let me go ahead and actually do that. I'll go ahead and add it to the end, right? This is going to be the end of the line, and this is the beginning of the line. Where do you get in the line? You have to go to the end of the line to wait your turn, right? Is full, is empty, none of this stuff changes, right? Peak now changes, because if we're putting things in on this end, the next thing to come out is on this end. And so, I guess this stays the same here, right? Because now we're operating on this end. Anywhere I said stack, of course, I will need to have a queue instead, right? But otherwise, that was it, wasn't it? That's it. There is no other changes. All I was doing was the stack operated on the same end. All I did here was change it so that one of the operations was at the other end, and I've got a queue. A fundamentally different data structure that gives you completely different properties. Again, it's now a first in, first out. When we come back, when we start looking at trees, we're going to look at two different tree traversal algorithms, so several different tree traversal algorithms. But one of them is DFS, one of them is BFS. And the only difference is whether or not you're using a stack or a queue. Right? And that one small difference makes an entire completely different computational thinking. Not only that, but you can actually prove that with a queue, you can simulate a stack, but you cannot simulate a stack with a queue. Right? It turns out that that small little tweak is so fundamentally different that it actually has implications for computability theory and what is computable and what is not computable. So it's really remarkable that one small change can completely change an entire data structure. Let's go ahead and make sure that it actually works here, though. So instead of a stack, I'll have a queue. Right? I'll call it queue. Right? Instead of pushing, I'm going to go ahead and say queue.enqueue. And did I rename it, by the way? No, I didn't rename it. It should have been dq. There we go. And while queue is not empty, then go ahead and queue.dq. Okay? So if I'm putting in I here, sorry, 0, 1, 2, 3, 4, then what order should I get them out in? 0, 1, 2, 3, 4. Right? Works. Okay? Excellent. So there's my implementation for a queue, right? Same design considerations and efficiency concerns as a stack, right? You can use a linked list to implement a queue. You just have to work at different ends. And you get a first in, first out ordering. Okay. So some variations on this. Some variations would be, of course, with a queue or a stack, you could have line jumpers. Right. So in real life, we don't like line jumpers, but of course, line jumpers are real life. I've never been to Disney World, or actually, no, I take that back. I've been to Disney World once when I was a kid, but I understand that, you know, long lines for the rides, right? How do you get out of those long lines? A fast pass, right? You pay more, and then you get to jump to the head of the line. And so you can have line jumpers in a queue, right? This might be called a priority queue, where the visualization here is you're not in order anymore, or you're not necessarily, you know, the first in, first out order anymore. Instead you have some sort of ordering, right? So 10, 20, 42, 30, 50, 70. Right? Looks like it's sorted to me. Now, when 5 gets n-queued, right, they don't go to the back of the line. Instead, they get to be line jumpers. They go, nope, I have a higher priority, and then I get to jump to the head of the line here. Now, the problem with that is that if I implement it just as a naive queue like this, then I'm doing a linear amount of work to find out where I belong. Maybe I should have started at the beginning. But then if I have a very low priority, 80, I would have to then go all the way to the end. So there are better ways of doing this, and we'll look at a better way of doing this called a heap later on. Right? Now, if you've got a different priority, say 30, right? Well, same idea here. You get to jump ahead, but not so much. Right? You get to go ahead and go between 20 and 30. Now, when you dequeue things, you always dequeue things with the lowest priority or the highest priority, whichever the case may be. Right? Why would you want to do this? Well, you want to sell fast pass at Disney World or whatever. But it also makes a difference with even something as simple as a Unix utility. Man, nice. Nice is a utility that you can alter a scheduling priority. So in a computer, you have various tasks, and those tasks, not all tasks are created equally. Some tasks should have a higher priority because without them, say, it's an operating system task. Without that task being executed, then the entire operating system could grind to a halt. So you have certain things that get to jump to the head of the line, have a higher priority, and these need to be done now. You have things that have a lower priority, like user programs, or maybe a database backup. A database backup is important, but it's not as important as serving the people that are actually using the system at the time. Nice is a utility that allows you to define a priority and say you can be nice about it and have a very low priority, 20, in which case anything with a higher priority you get preempted by it. Or you can be very, very greedy about it and have a priority of -20. Right? And eventually you'll get executed if you have a low priority, but you're allowing other people to go ahead of you that are more important. Right? And that is a priority queue. Right? Again, the efficient implementation of a priority queue is going to be a heap. We'll talk about those when we talk about trees. Right? One of the last things that we'll talk about. Okay. You can also have something called a double-ended queue, or it's called a DEQ, D-E-Q-U-E. Right? It is spelled that way, and it is pronounced DEQ. So unlike a queue where you've got NQ and DQ, in fact, I should have written those operations. Operations is NQ. Sometimes this is called push. Sometimes this is called offer, and DQ. Again, sometimes this is called pop. Sometimes this is called pull. Right? Some other languages might use different terms for this, but those are common. Right? So a DEQ is a double-ended queue, where you can operate at both ends. Right? You can insert or remove at head and tail. Right? So now think about this. Why would that be an even better implementation? DEQs, D-E-Q-U-E, right? DEQs can be used to simulate a stack. Stacks and queues with one implementation. Right? In fact, in Java, I wrote a stack and a queue implementation, but Java doesn't really have, Java does have a queue implementation, I believe, and a stack interface, but don't quote me on that. It doesn't really matter because Java encourages you to use instead a DEQ. Right? And there are two implementations of this, an array DEQ and a linked list. So why a linked list? Because it operates at the head and the tail, and you can do both of those. So let's actually look up the documentation for this, a Java DEQ. So remember all those design considerations that we came up with? Well, what about bounding it? What happens when you try to put something in a full data structure? What happens when you try to pull something out of an empty data structure? How do you know what to work on one end or the other? Well, guess what? A DEQ takes care of them all, right? If you want to insert, remove, or examine, in other words, examine is peek, right? If you want to operate at the head and you want a method that throws an exception in the event of an error, then you use add first, remove first, or get first. If you want to operate at the head and you want a special value to be used instead of throwing an exception, it'll return null, or it will be a no operation or something like that, right? Then you use offer first, pull first, and peek first. Likewise, if you want to operate on the tail end, then it's add last, remove last, get last, or offer last, pull last, or peek last, depending on whether or not you want a special value or you want an exception to be thrown. So if you're looking for a queue, then all of these methods have an equivalent DEQ method. Offer is just offer last. Remove is remove first, right? It's operating at two different ends efficiently. If you want to push and pop, and you use add first and remove first. Of course, those are just suggestions. You could always work at the other end, right, if you wanted to, as long as you're consistent about it. Okay. There may or may not be some other considerations in here, but all known implementing classes here. Those two in the middle, by the way, are thread-safe versions. But otherwise, there's the array deck that I was talking about. What do you think it holds elements? How do you think it holds elements? With an array, right? And there's the linked list implementation. Right? So over here, instead of creating our own queue, we would create a deck, right? And we would create a, say, new linked list. Import both of these to make it work. Import deck. And we've already imported linked list, so we're good. Right? Now I want to enqueue something, so if I want to treat it as a queue, I want to add last. Right? All right. Queue.add, or I could just add if I want to. There we go. And if I wanted to dequeue it, note here I didn't have to change this. It has its own isEmpty function. Right? And if I wanted to remove it, then .remove. What is it? Remove last. Pull. I could just go ahead and go with pull. Queue.pull. There we go. Now this is again adding 0, 1, 2, 3, 4. And so if I pull those all out, 0, 1, 2, 3, 4. Didn't have to do my own implementation at all. Without changing a single line on 13 or a single character on 13, I can go ahead and change, well, here, I'll change it to S because it's going to be a stack now. If I wanted to change treat it as a stack, I could add something, add first, and then .remove first. Or is it pull first? No, it's remove first. And now if I put in 0, 1, 2, 3, 4, and I treat it as a stack, then I should get 4, 3, 2, 1, 0. 4, 2, 3, 1, 0. Not only that, but it allows me to work from both ends in different combinations, right? So consider, what if you were able to push at both ends, pop at one end? Right? That's a very simplified version of our priority queue. Right? So think about this visually. What if I were able to, here's the front of the line, and here's the front, and this is the back. Head, tail, whatever you want to call it. Right? Suppose that I was able to push at both ends. I could push things in here, or I could push things in here, but I only ever took out of the front. Right? That's a very simplified version of that fast pass, right? Where we've got line jumpers that they don't just jump into one part of the list, they always jump to the head of the list. Right? They preempt everybody. What about another variation where I am able to pop from both? In fact, I want to redraw this. Let's create a new one here. I want to pop from both ends, but push in one end. And now the use case that I'm going to give you here is a very common one. Think about writing in a Word document, right? So you type, you delete, right? You copy, paste, you type, you delete. Oops, I didn't mean to do that. What do? Control Z, Apple Z, it is undo. How do you know what the last action you did was? There it is at the top, right? Undo. Once that's gone, well, oh no, I also need to do another undo. Undo, 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 undo. Right? How do you know the sequence of actions that you took? You're using this stack as a breadcrumb tracker, right? And every time you do a new operation, you push that operation. Every time you do undo, you pop that operation. Right?
How would you do a redo?
That's a good question. Probably wouldn't want to just pop it. You would probably have some sort of a pointer, right? And then you have things going both directions, and then you move this up and down, right? If you want, I don't want to get that fancy though. Let's just do the undos first, and then we can worry about that. Why would you care about popping things off the bottom?
Space.
Space considerations, right? This is a bounded deck, right? And say that we only keep the last 10 actions that you did, right? And then the oldest fall off first. That sounds like an LRU cache to me, right? So another consider push at the, pop at both ends. Push at 1, right? An undo stack, right? Or an LRU cache, right? An LRU cache is a kind of a least recently used cache, right? So it's a way to store things, but you can't store everything. So you have to be judicious about what you store. And one way that you can do that is, well, the oldest thing, that I need room. I need to store this brand new thing. What I'll do is I'll get rid of the oldest thing. Right? And if your oldest thing is at the bottom of your stack or your deck in this case, then it can fall off automatically. And it just gets pushed off and thrown away. Right? I should say popped off and thrown away. So those are all variations that you can implement and that have different use cases and stuff like that. Okay. What are some applications of queues, by the way? Applications. Buffers. Right. So for those watching at home, okay, I am the only one watching, so. Those watching later, of course, you'll have an entire hour lecture, right? And here you are in YouTube, right? And it's loaded up the entire video, right? Maybe not the entire video since it's streaming, but say that you've got the next 10 minutes loaded up. Where is that data being stored? In a buffer, right? The first frame to come in, it doesn't really work like this, but this is the idea. The first frame to come in is the first one to be consumed and displayed, right? And if any time that you want to store things, storing things in order, right, is a perfect use case for a queue or as a buffer. Right? This is also common in producer-consumer patterns. I briefly gave an introduction to this when we did multi-threaded programming. One way that you can visualize this, though, is, and I think, did I display the picture for it? You have a bunch of producers. They're all asynchronous, right? So this could be like people making requests to a website or something like that. And they all make requests that need to be serviced by your program or something, right? Well, we can't do them all at once because we don't have all the resources, right? So what we do is we store these requests or tasks in a queue, right? It could be a priority queue, like you have higher priority tasks or whatever. And then you have independent consumers whose task it is to go here and ask for some work. Yes, I can now service that task, right? Once you're done, then you come back and you ask for more, right? And they consume off of the other end of the queue, which is being used as a buffer here. And since this is all asynchronous, you want some sort of a balance. For example, what if you didn't have enough consumers and you had a lot of producers? What would end up happening? A lot of wait time, and eventually your buffer gets full, right? And it all grinds to a halt, right? What if you had too many consumers and not enough producers? They just get popped off immediately, right? Then you have an empty queue, and you've got idle consumers over here wasting resources doing nothing, right? Think about this as a bank and tellers, right? You've got customers coming in. You've got bank tellers taking care of those customers, right? Well, you could always make sure that all the customers are served immediately by making sure that you've got your like two or three times the staff that you need. Is somebody going to pay for that though? Right? No. So what you want is a nice, perfect balance, right? And that's where queuing theory comes in. And then you can define all these nice Poisson distributions on incoming requests And if you have this nice distribution, that tells you exactly how many consumers you need. You can even build in models where, you know, if there's somebody that's been waiting for 5 minutes, like if they wait for X minutes, we know that they'll leave and we'll lose a customer or something. And then you can build in that tolerance. Well, we're okay with that because losing a customer is not as expensive as paying somebody to be there to service that customer, right? And you have this nice equilibrium that you can figure out by looking at queuing theory. All right. All right. Any questions about lists or list-based data structures? No? Then this marks the point where we're going to get into more theoretical stuff. It's not that theoretical, but here, let me go ahead and bring this up and open a new window. All right. But we're going to start developing a more formal framework for quantifying when one algorithm is better than another algorithm. Okay? And the motivating demonstration is just going to be a repeat of a lot of the demonstrations I've already given you. But it's going to even be even simpler than that. Right? So let me go ahead and close this, and close this. And let's look at this list demonstration. Okay? I'm using this big integer class because I'm going to be adding up a lot of numbers that sum to more than 2.147 billion. And so I'm using this arbitrarily large number built into Java here. What does it do? It takes a list of integers, numbers. And all it does is it iterates over that list, right? Gets the ith one, converts it to a big integer, and adds it to the result, reporting this result right here. Okay? So let's just go ahead and start out with 10 values here. They're all random values, okay? This one just builds this list, which is initially a linked list. And then I sum up how long it took me to, or I add up I time how long it took me to sum all those up. So let's go ahead and run this and you'll see that, okay, so it's kind of a large number, right? But it took a very small amount of time, right? That is a -4 there, so we're talking about 0.00028 seconds, okay? So let's bump this up to, say, a new baseline here, 10,000 elements, okay? Let's run it. 0.06 seconds, essentially. Of course, you'd want to run this over and over again and get an average and then take the average. You'd also want to run this in isolation. I'm running OBS right now, which is pretty computationally expensive, even though it claims it's not. It starts my fans running, which is why I bring this all the time. But anyway, there's 0.6 seconds. What if I went up one magnitude? Right? 10 times as big. Well, ideally, you'd think that it would only be 10 times as slow, right? 10 times as slow in this case would be 0.6 seconds. So let's run it and find out. We're way past 0.6 seconds. All right? Almost an order of magnitude squared. Squared, right? Slower. Right? What if I went up to 10 million? Or is that 1 million? Right? Now that's an order of magnitude 10 times greater. Right? And ideally, this should only take 40 seconds, but based on what we just saw empirically, it's going to be 100 times slower. 100 times slower here is going to be 460 seconds. Let's just go ahead and run it. 460 seconds is how many minutes? 300 is 5 minutes, so 7 or 8 minutes. Okay. Well, you'll be glad to know that I've already done this. Right? In fact, I did it for many operations, and I think I averaged them too. So let me just go ahead and show you what the graph of this looks like. Bear with me while I open it. There we go. Here's my PDF. This is the same graph that's in the book, by the way. There we go. So there are all my samples. And I went up by orders of magnitude here. These are thousands. So 200,000, 400,000, 600,000. Here's 100 1,000 thousands, we call them millions, right? And that's what I'm running right now, right? And it turned out to be about 500 seconds here, like I said, 460 seconds or so, right? And, it wasn't, sometimes it was higher, sometimes it was lower, but that's all sampling errors. This red line right here is a quadratic regression. So you've probably heard of linear regressions, but if you've got a bunch of sample points and you want to determine, well, what linear function matches those points closest, right? You can do a linear regression and find that. You can also do a quadratic regression because I posited that the behavior here looks like a quadratic function to me. It doesn't look like a nice sloped linear function. It looks like a quadratic function. And so I derived a quadratic regression, and look at how nicely that fits, right? That gives me pause, or it doesn't give me pause, it gives me evidence that this is in fact a quadratic algorithm, okay? This naive algorithm that we are running, and let's see, is it still running? Yep, it's still running. We'll see if it's actually correct, right? Over here, right? So this linked list index of method that we're using over here to get the ith element is actually quite inefficient. Why? Because of that painter, right? If you want the ith element, what do you have to do in a linked list? You have to start at the beginning and traverse all the way to I, right? Let's actually, while we're waiting for that to run, let's think about that mathematically, all right? So on the first iteration of that loop that I'm just simply summing things over, right? On the ith iteration, when it's 0, what is the number of traversals that I have to do to get to that one? 0, because it's right there. On the second iteration, how many traversals do I have to get to the second one? 1 to get to the second one. On the second iteration, I have to go start at the beginning, 1, 2 to get to the second one. Right? That should tell you what the pattern is. On the ith iteration, I traversals, ... When do we stop? On the n-1th iteration, there are n-1 traversals. Right? What is the sum total of traversals here? So this is going to be, we'll go ahead and ignore 0. Why? Because 0 plus whatever is whatever, right? So let's go ahead and sum all of these up. What is the sum of 1 plus 2 plus 3 plus 4 plus ... plus n-1? You might have seen this before. I starting at 1 up to n-1 of I. Right? That's a summation.
N squared.
Okay.
Probably.
Yeah, it's something like that as an aside over here. In general, if you go I is 1 up to n, we're off by 1. This is
n times n-1.
n times n-1
Over 2.
all over 2. Do you know what that's called? Gauss's formula.
Yeah.
Right? Why was it called Gauss's formula? Because of Gauss. You're right. Gaussian distribution, Gaussian elimination, right? Normal distributions. Actually, Gauss is not normal distribution, but anyway, the folklore story, I don't think it's actually true. I think it's just apocryphal. That is that he was a child prodigy, and his tutor or his teacher told him just to get, he was bothering him, so to get him out of their hair, he said, add up all the numbers 1 to 100, and so he said that it was 100 times 99 divided by 50, and he derived that formula so that he didn't have to do all the grunt work, right? So if I plug this in over here, what do I get? Instead of n, I'm using n-1, so this will be n-1, n-1, minus 1, so it'll end up being n-1, n-2, all over 2. Right? Yeah. So, distribute everything here. It doesn't matter. N squared all over 2 plus, and then I'll leave these lower order terms over here. Who cares? Right? In fact, who cares about this 2 right here? Right? That's eventually where we're going to go with this. We're going to ignore lower order terms. If I took a a limit as n increased, what would be the most important term in this entire expression right here? It'd be n squared, right? In fact, dot, 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 eventually we'll say that this is order n squared, big O of n squared, okay? So not only does my empirical measurements tell me that it's n squared, but my theoretical analysis of this algorithm is telling me that it's something like n squared, right? Is it still done? Is it done yet? It's still not done, okay? We'll find out, right? So for the naive approach, it requires about n squared traversals. The algorithm in this case, the underlying operations that we're doing here, are a quadratic algorithm, and it's extremely slow, right? To provide some perspective here, right? So perspective on this. Right? Every time, so here's the actual quadratic regression that I did. And these are the actual coefficients here, right? So the first coefficient is 6 times 10 to the negative fourth times n squared, minus, and then another very small coefficient here, plus 9, right? This is t, this is quantifying time, right? So there's some cost to just doing business, basically, right? But also, depending on how big your list is, right, then that factors in with this coefficient here, and it also factors in a square term with this coefficient right here. Why is that coefficient? Oh, that coefficient's extremely small. Who cares, right? That's 0.0006 seconds times n squared. Right? But when n is big, n squared is even bigger. And now it starts to become 400 seconds, 500 seconds, right? And minutes turn into hours, hours turn into days, days turn into weeks, and weeks turn into, quickly, centuries. Orders of magnitude greater. Right? But why is this coefficient so small? Well, it's a computer. Computers are fast, right? Each individual operation is extremely quick. What this is quantifying, however, is the total number of operations. And if the total number of operations is large, it doesn't matter how quick each individual operation is. They all start to add up, okay? That's the actual regression that I ran on this whenever I ran the experiment last, right? And note that it has a coefficient of 0.994. The best you can do is 1, a perfect quadratic function. You can fit that, if all the data fits to that, then the coefficient would be 1. All right, so 0.994, that's as close as it gets. And visually there, look at that, right? It's so close. Now, what's the solution here, by the way? Don't be that dumb painter, or the smart painter if he's getting paid by the hour, right? Instead, what should I do? What's the fix here? Do an iterator pattern, right? Or better yet, an iterator pattern in Java is simply going to be a for integer x in numbers, right? And don't get the ith value. You've got it right there. You took your paint can with you as you went along. Right? It's still, okay, I'm just going to kill it. Trust me that it's going to run for 8 minutes. I think it's been 8 minutes though already, right? I don't know. Anyway, there's the same 1 million random integer numbers in the blink of an eye, 0.1 seconds. Right? If I went up an order of magnitude here to 10 million, predict now how long it's going to take. I went up an order of magnitude, so 10 times as big. It's only going to be 10 times as slow, about 1 second, right? Once it gets done. Right? In fact, it's less than that. Right? Why was that? How is that working if I'm going along each and every single time? So, same analysis here. On the ith iteration, there were 0 traversals. On the next iteration, how many traversals were there? 1, because you were already at the first one, you just go 1 step to the next one. On the second iteration, or third iteration, how many traversals are there? Just 1 more, because you're already there, and you just go over 1 more. 1, 1, you see the pattern now? dot 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 I. How many? 1 dot 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 n. Yeah, n minus 1, I guess. And that's only 1 as well. So now what's the grand total? That's even easier to do. N minus 1. What's the pattern here? What's the most important term here? It's just n. And eventually we'll get down that this is linear instead of quadratic. Right? So every time you go up by an order of magnitude of 10, you slow down by a magnitude of 10. Like it takes you 10 times as long. Here, if you go up by a factor of 10, it takes you then 100 times as long or 100 times slower. Yeah?
Can you show again the original code that was slow?
Yeah. I'm using the get I method right here. Now, if this were not a linked list, if this were an array list, then it wouldn't matter because we can magically jump using random access to not do much work. Right?
Because you get I iterates.
Yep, exactly. Right. Let me go ahead and undo that. Now, in case you think that this is a contrived example, up until like 8-10 years ago, whatever it was, I was using contrived examples until I saw this extremely stupid code in an actual project that somebody was touting as, oh, this is a great open source project. I go, okay, well, let me take a look. The first thing that I looked at was they had a general list, it was Java, they had a general list here, and they were using this kind of loop and get I. And I knew they don't know what they're doing. Right? Now, granted, that project never probably had to deal with big data, right? So it never manifested itself as, oh, this is taking 5, 10, 20 minutes to compute here. They only ever had lists of 50, 60 things, right? And when you're looking at the lower order values over here, it doesn't really matter, right? That's all the same over here. It's only when you get to these larger and larger and larger lists over here that it starts to matter. So they got away with it, and I knew, no, if you want me to, I'll go ahead and put in a pull request and tell them, don't do that, right? And then, of course, you'd probably get back a snarky, well, yeah, but we never have data that big, right? No, you shouldn't be writing a for loop like this in Java anyway. Java, at least in the last 15 years, you should be using an enhanced for loop. Okay, so not a contrived example. It's an example that we see all the time, right? And variations on it, okay? So again, if you were to take this and extrapolate out further, the graph only goes up to 1 million, right? What if we went up to 10 million? That is, what if I took this, this expression right here and substituted in 10 million for n? What do you think it would look like? Big. How big?
Really big.
N equals 10 million. It would take 17.59 hours, right? On whatever machine I was running. Now, those experiments were probably run on my old Mac, which was an i7. Maybe it was an i9 as well. I don't know. But it was this one is definitely an improvement. What if I did 100 million? I went up an order of magnitude further. 1700 hours, which is 74 days for those that can do that math in their head. Right? What if I went up to 1 billion? That's just one order of magnitude more. 74 days turns into 7,400 days and 20 plus years. So we're into decades. Right? So you don't have to be exponential to get into unrealistic computational times. All you have to do is be inefficient, and for a sufficiently large number of elements, by the way, 1 billion is not big data, right? 1 billion that's nothing, right? You could have 1 billion logs in the matter of an hour in a moderately sized web server, right? So that is not big data at all, right? But 20 plus years, that's not at all acceptable. What about that linear solution? Right. Again, I could have graphed it along with this, but I didn't, because what would it look like? It'd definitely be a linear line, so it'd be a linear function, but you wouldn't even be able to see it. Why? It would just follow the x-axis. Right? That even for 1 million elements, 1 million, I think it would be less than, what was it? But we did it. What was the number? You tell me. What was? Oh, well, that was 10. That was 10 million. So it would have been like 0.6 seconds. 0.06 seconds. 0.06 seconds. Right? If I go up to 100 million, then it'd only be 10 seconds. Right? Oops, sorry. And if I went further to 1 billion, well, 100 seconds times 10 is going to be about 100 seconds, about 2 minutes. Right? 2 minutes versus 20 plus years. Right? So the takeaway on this introduction to algorithms and algorithm analysis is these things matter. Right? You'll always see folks, you know, when in the actual workplace. Yeah, we went over big O analysis when I went to college, or when we did this, but I've forgotten it all now, right? If you forget the theoretical analysis, fine. But if you forget that data structures matter, find a new line of work, right? That these things do matter, even for small things, right? All right, so what we're gonna do now is the thing that you will forget about, big O analysis, right? We'll eventually get there. It should be clear that programs cost resources. So you tell me, what are some obvious resources that it takes to run a program? CPU time. So I'll just go ahead and go with time. Either real time, CPU time, etc. Right? CPU cycle, CPU time, CPU cycles. Right? GPU type, GPU, cycles, whatever. Right? That's an easily quantifiable resource. What are some other resources? Memory. Right? That's the other obvious one. Right? Is this going to require more and more memory? Right? For example, if I kick this up to, I don't know, what is that? 100 million. 10 billion. I'm not going to be able to do that with a simple integer, so I'll change this into a long. There we go. I'm sure after a few seconds here, it's going to tell us that we're going to run out of heap space. Eventually, maybe. All right, well, we'll let that run until it dies. All right. So there might be some memory considerations. Now, put on your engineering thinking cap. What else does a computer cost? Power consumption. Right? Some shun. Would you need to buy a new phone? For the same price, you can buy a phone that is twice as powerful, or you can buy a phone whose battery life lasts twice as long, because its power consumption is half as much. But it's not. It's the same power as your current phone. Which do you want to do? Battery? All right, because your phone's fast enough, right? It's not like you're going to be running like Halo or whatever games people play on your phone, right? A phone, you have power consumption considerations that are far more important than time or memory, right? What else? Think networking. Network, throughput, right? How much data you can push through the network, and bandwidth. Right? In fact, that's often the bottleneck. Your computers are going to be faster than any data that you can send over the wire. Right? Say what? Oh, there we go. Yep. Java heap space. I ran out. You cannot do, what is that number? 10 billion. You'll eventually run out. 10 billion times 4 bits, that's 40 billion, which is 40 gigs. Yeah, that's how I run out. I think I've got, well, virtual memory, I've certainly got that much, but the Java virtual machine was not allowing that much. And my fans are going nuts right now, so. Right. There's another resource, right? Heat dissipation, or heat dissipation, right? That, yeah, it could, I don't know, if you go to a large server farm, they're paying more for power to cool everything than they are to actually run their machines. And that's why they like to do a lot of stuff in the Midwest here, because power is generally cheaper, and you like to do it in a colder climate because, you know, it's easier to cool things, right? In fact, there was a bit mining operation in Norfolk or somewhere. They moved from China to here. It's a commercial bit mining operation that was on the news of some sort. And they moved here because it's cheap, and because they wanted to escape any lockdowns in China and you know, crackdowns on Bitcoin mining, basically. We have no such concerns here. Yeah.
Why is it that computing makes a computer
Well, it's wasted power, right? If you're sending electricity through a wire, right, then you're losing. I mean, ideally, you wouldn't lose anything, right? It would be a closed system, and that power would just keep going. But running it through a wire, it's going to heat up, right? And that adds up, and you have to dissipate it somehow. You have to cool it down. Right? Yep, physics. All right, so heat, it could be, or more to the point, heat dissipation would be your resource that you would have to expend. Right? If you were talking about an embedded system, the number of wires or gates in a circuit. Right? Another one that is not commonly thought of but should be is idleness, right? Or utilization. That server farm that you built. Wow, we bought 10. We say that we bought 10,000 3080 or 3080 Ti's, right? But then we don't do anything with them. They're just sitting there idle most of the time, right? That's a lot of hardware being purchased and it's not being used, right? That's when you, of course, fire up your bit mining operation and let it run 24/7, 100%, and hope that the amount that you mine it will exceed your power costs and your hardware costs, right? That's why you have to inflate the price of Bitcoin so that it makes it worth it. But idleness, another situation would be, does a small department on our campus require an entirely dedicated web server on dedicated hardware? Right? Not many people are going to go to, I don't want to pick on anybody in particular, so the basket weaving department, right? Not many people are going to go to that website. So do they need their own hardware? No. And so it'll end up being wasted resources because it's sitting there idle most of the time. And the way that you solve that is through virtualization, right? You can run 20 different virtual machines on one piece of hardware, right? And the utilization goes up, idleness goes down, and your resource is saved, right? In that sense. So which one of these matter more than any others, right? These are all extremely important. This is why I asked you to put on your engineering cap, right? Important engineering considerations. Do we want to analyze our stuff with respect to any one of these, though? Probably not. Why? Because an algorithm is an abstract idea. It has nothing to do with computers. Right? Go back centuries to Gauss, or not Gauss, you'd only have to go back a century to Gauss. Euler. Euler, his GCD algorithm, right, is more than almost 2,000 years old. Right? Now, because we have modern computers, doesn't mean that it's any more efficient than it was 2,000 years ago. There is still the same number of steps to compute a GCD, greatest common divisor, right? There's still the same number of steps to compute a greatest common divisor. It's just that we can do it a lot faster using a computer now. But a computer still does, say, 10 steps that it would take you to do the 10 steps on a piece of paper. Right? Algorithms are invariant. It doesn't matter about any one of these things. Algorithms are a mathematical idea that are independent of any hardware that you're running it on. Right? If you upgrade your hardware to be twice as fast, your algorithm is not twice as good, right? It remains the same, right? There are the same number of steps involved regardless of the hardware you run it on. Let's go back to this, this equation up here. If I upgraded my hardware and reran this experiment, what would change here? Would the n squared change? Nope. Would the n change? Nope. Only these three coefficients here would get better. If I went to hardware that's twice as fast, then this would be 6.41 e to the negative 4 divided by 2. Right? Now that's a hand-wavy way of doing it, but that's essentially what it would be. It would still be n squared, right? And it would still take me 20 years, oh, maybe divide by 2. Instead of 20 years, now you get 10 years instead. Right? Is that an improvement? No. Right? That's only an improvement in hardware. Okay? You want to analyze, our goal will be to analyze algorithms independent of any particular hardware, language, or other engineering consideration. Right? Now, that's not to say that engineering is not necessary. Of course, absolutely. When you actually go to build something, you look at all those things above and you start to consider those things. One classic example is Garmin hasn't visited because of the pandemic in a long time, but it used to be that Garmin would send a representative every year, and to try to recruit people, of course, but also to give an idea of what they do in practice. And I always ask them to do the same presentation because this guy, they had a choice of sorting algorithms. They could choose between quick sort, very quick, or bubble sort, very, very slow, right? But on engineering consideration meant that memory access was way more important than CPU time. So they made the decision to choose the slower algorithm that was actually less intensive on memory. Fine, it's slower, but our bottleneck is memory, right? It's an embedded system, it's a Garmin system. We have no tolerance for wasted memory, and quicksort would have wasted memory. Right? So they chose a slower algorithm because their consideration was memory. You said that you wanted a phone that was slower, but lasted twice as long because of the battery, right? That's because you were thinking like an engineer, a consumer engineer, right? And so you were willing to trade off somewhere, right? Our goal, however, will be to say that this algorithm, whatever work it's doing, we call that an elementary operation, we want to know how that will behave as input sizes grow, right? And that's going to be our ultimate consideration, right? What matters is the performance of the algorithm with respect to the input size. Right? I don't want to type that, so let me bring that over. Not any particular machine language, architecture, etc. To go back to what I was saying before here, language. If time was your greatest consideration, what language should you choose? C. There you go. Right? Python? Nope. Python is going to be orders of magnitude slower on anything that you do. Right? So the closer you get to the actual metal on the hardware, the better you're going to be. Right? Of course, at that point, you should start looking for better solutions like multi-threaded programming and stuff. How can you split up your work and then farm it out? Right? Or maybe you just don't care because you're only ever going to have a list of size 20, right? Like those folks that I was talking about before.
How do they only have a list of 20?
Well, I mean, I think it was a medical record system, and an individual is not going to have thousands of individual records, right? Their immunization records, a couple dozen, surgeries. If you have had thousands of surgeries, like, whoa, okay, you're the bionic man right there, right? You know, it never came up as a use case, right? They never had to do any load testing and try to, you know, break the system with so much data. Right? We're only interested in the growth rate of resources consumed by the algorithm as they tend towards infinity, right? For that reason, we want to look at a resource function. That's not what I want. There we go. Come on. Face ID, sorry. All right. There we go. We're going to want to look at what it looks like when we go from small input sizes to large input sizes and the growth rate of this function, right? Mathematically, that means that we're looking at, and hopefully you've had 235 or you're doing 235 right now. We're looking at a function that maps the natural numbers to the positive reals. Okay? So the natural numbers, why is our remember that these are called the domain and codomain? Domain. This is the codomain. You've done this in 235 or so, right? Or before that maybe? Yes? Yeah, okay. All right, good. What are the natural numbers? Well, first of all, you tell me, what are the natural numbers?
Positive integers.
Positive integers, 1, 2, 3, ... I left some room there. Why?
Including 0.
You include 0. Right? If you don't include 0, you have the counting numbers, right, from grade school. And you start at 1. But without 0, you don't have an additive identity, right? 9 plus 0 is 9. You need an additive identity for this to become a group or a semi-group or whatever it is. Right? Anyway, who cares? What is this capturing? What is this modeling? It models our input size. Right? So why did I choose the natural numbers? Can you have negative values? No. A negatively sized array? That doesn't make any sense. Can you have fractional values? Can you have an array of 1.5 things? No, that doesn't make sense either, right? And so you can, of course, have an input size of 0, right? There's nothing, right? That's perfectly fine. What about our codomain? What is that modeling? The reals are what? Are, you know, all x greater than 0. Right? And so that's fractional values, that's irrational values, that's whatever you want. What is it modeling? It's modeling, say, for us, say it's time. Right? Now, can you have negative time? No. That'd be awesome, right? You start your algorithm and then you got your answer last week. You were literally time traveling, right? Weird, but I mean, the quantum entanglement, maybe, right? Star Trek kind of stuff, right? So that's why we're looking at this, this model right here. We're looking at a function, and I'm not even going to call it f anymore. I'm going to call it t, because it's going to be time. Right? Given an input size, how much time does it take? For this particular algorithm, from an empirical analysis, it looks like this. Right? What are some other functions that you've seen before with respect to, say, algorithms? Or just in general, functions that you've seen before in, say, math. I'm drawing my x and y axis like this, right? Y, this is the input size. N. And this is, say, the time. Right?
Logarithmic.
Okay, logarithmic. What would that look like? It's monotonically increasing, but it flattens out, something like that, right? Log. Now, what kind of log? There's certain, that's the natural log. That's log base 2. You can also have log base 10. So which one is that? Yeah, it doesn't matter, does it? Why? Because of the change of base formula. Log base b can be changed into log base a of n by taking log base a of b. Right? In other words, it's just some constant sitting out front of log b, or a. Right. And do we care about constants in the end? Probably not. Because upgrade your hardware, and whatever constant you had before is now half as much. Right? What other kind of, so this is log. I'll just write it as log. And because we're self-respecting computer scientists and not mathematicians, we know our log base is what? 2, binary. Right? This is regular people, right? Normies. Math folks are what? ln is here. ln is log base e. Why? E is 2.71, blah, 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 blah. There you go. Because that's the value for which, when you take the derivative of e to the x, what do you get? E to the x. Right? Any other base, and you will get some coefficient sitting out front here. And that's messy. Right? But that's mathematicians. That's why they call that's not, it's anything but natural. It's only natural when you consider the first derivative. Right? What other functions? Linear? Right. And what is the most general form of a linear function? A, in this case I'm going to go with n because that's what my domain is, plus b, where a and b are coefficients, some values. Right. And the slope of this is determined by a. But again, that is a coefficient. Your slope can go down, and you can take this, and then it'll go down, go down, go down, go down, with faster and faster hardware. But what about the growth rate of this? Now you're all in calculus, so what's the growth rate of a linear function? A n plus b. Yeah, how do you get the growth rate of any function? The first derivative. And that's going to be what? A. Right? In other words, it is growing by some constant. What's the growth rate of a log function? 1 over n with some coefficient over here, right? Because if you take the natural log, 1 over x, 1 over n, and then there's some change of base formula or whatever. In other words, tell me about the growth rate. As n gets bigger and bigger and bigger, it gets smaller, and the growth rate itself gets smaller and smaller and smaller. That's why it tapers off, right? Because it gets smaller and smaller and smaller. The growth rate of this function, of course, is a. What about the growth rate of n squared? A, and the most general form of this is going to be an squared plus bn plus c. First derivative of that is going to be 2an plus b plus 0. So forget all those. Guess what? The growth rate grows as n grows. The growth rate stays constant. The growth rate goes down. The growth rate grows with the constant, with n, right? And you can imagine that it's going to be even worse as you go up in polynomials, right? So, n squared, n cubed, right? Dot, dot, dot. You can even get into 2 to the n. That's going to be exponential. What's the growth rate of an exponential function? We already did one. Itself, right? The growth rate of an exponential function, we'll just go with, like, say, 2 to the n. Right? This will end up being some constant coefficient out front. It's going to be the natural log of 2, but you didn't get anywhere. 2n stays. In other words, the growth rate itself is exponential. Right? So, no. There is your orders of magnitude, right? Better and worse. Or worst, worse. There we go. All right? And we're going to use a tool called Big O to get rid of all those constants and say that things are, the functions that we've looked at so far are going to be order log n. Right? This is logarithmic. Order n is going to be linear. Right? Quadratic. Cubic, or in general, order n to the k is going to be polynomial. Why? Because that's a polynomial. Right? What about order 1, where it's just like, say, a formula computation? That's going to be constant. Right? And then we can also have order 2 to the n, which is exponential. What's even larger than that, now that I've run out of room? Super, yeah, that's super exponential. Order, give me an example.
Isn't it like there's a tree operation or something?
So A, B, C. How many ways are there of arranging those 3 letters? A, C, B,
Factorial. Oh,
B, A, C, B, C, A, C, A, B, C, B, A. Right? These are permutations. We've done that in 235, right? Maybe not yet. Right. How many are there? Well, in that particular case, in general, factorial. Right. Take a 52 card deck, shuffle them up. How many different shuffles are there? 52 factorial. That's already orders of magnitude greater than the number of atoms in the known universe. Right? So, nope. Can you do any analysis on the number of 2 pairs that you can do using a computer and exhaustive search? Nope. Right. So, and then you can go, you can get even above that, like the Ackermann function is not even computable and stuff like that. So, that's the foundation and the framework for which we will start establishing all these things. How do you go about, here's your algorithm, how do you go about actually analyzing it? It's a simple 5-step process. You identify the input size, you identify the elementary operation that you want to analyze with respect to, you analyze it with respect to that elementary operation, and then finally you provide a big O asymptotic analysis. Right? Simple. All right. Remember on Thursday we do have our SAP. Did I talk about this already?
Yeah.
Okay. So free pizza, and come and learn about the department, voice your opinion. Even if you don't voice your opinion, you can still talk to one of the student advisory board folks and give them your opinion anonymously.